Each number has a unique prime factorization, so we're going to count the prime factorizations of all possible products of our n dice. When we multiply our n dice, the prime factorization of the product will consist of some number of 2s, 3s, and 5s. We'll start by examining the 5s. The power of 5 in the prime factorization of our product can be anything from 0 to n. 0 if none of our dice shows a 5, and n if all of our dice shows a 5. Let's let d be the number of dice that do not show a 5. So d is going to be n minus c. So if c is equal to n, this means the prime factorization of our product is going to be 5 to the n, and d is equal to 0. If c is equal to n minus 1, we're going to show n minus 1 of our dice are going to show a 5, and we'll multiply that by one more roll, so d is equal to 1. If our prime factorization has 5 to the n minus 2, we're going to multiply this by 2 additional rolls, so d is equal to 2, and so on. If only one of our dice shows a 5, our prime factorization is going to include one 5 only, multiplied by an additional n minus 1 rolls, so d is equal to n minus 1. And finally, this is the case where we have no 5s. We'll be multiplying n rolls together, and d is equal to n. This count here, from 1 to n, these are rolls that are not a 5. So we're going to continue by doing casework on D. So let's examine our D dice that do not include a 5. Here are D dice that are not 5s, and we'll begin by asking what are the possible powers of 2 in the product. If all D dice consist of odd numbers, then our product can have 2 to the 0. If we have 1, 2, and the rest of them are odd, we could have just 1, 2 in this prime factorization. If all d of our dice show a 2, then we can have 2 to the d. Also, if we have 1, 4, and the rest of the dice show 2, then we can get 2 to the power of d plus 1. If 2 of our dice have a 4, and the remaining d minus 2 dice show a 2, then we can have 2 to the power of d plus 2. If all of our dice show a 4, this gives us our highest power of 2, 2 to the power of 2d. So these are all the possible powers of 2, and now we'll do casework on these powers of 2. And for each case, we will calculate how many possible powers of 3. And we'll start with 2 to the 0 power. If all of our d dice show a 1, then our prime factorization can be 2 to the 0 times 3 to the 0. If we have one fewer 1 and replace it with a 3, then the prime factorization is 2 to the 0 times 3 to the 1. We can replace all of our 1s with 3s until we have no 1s and all of our d dice are 3s. Restricting ourselves to the case where we have no 2s in our prime factorization, we have d plus 1 powers of 3. Now we'll count the number of powers of 3 when we have just 1, 2 in our prime factorization. If we roll 1, 2, and the rest of our d minus 1 dice show a 1, then we can get 2 to the first power, 3 to the 0. If we replace one of these 1s with a 3, then we get 2 to the 1, 3 to the 1, and so on. Here's 2 to the 1 times 3 squared. We can replace all of our 1s with 3s to get a power of 3 to the d minus 1. We can get another 3 by turning this 2 into a 6, and the rest of them are 3s. We still have 1, 2, and now we have 3 to the d power. This again gives us d plus 1 powers of 3. Let's take a look at 2 squared. For our lowest power of 3, we could have a couple of dice rolls that are 2, and the rest of them are 1. This gives us 2 squared times 3 to the 0. We can change one of our 1s into a 3, which gives us 2 squared, 3 to the first. We can convert the rest of these 1s into 3s. This is 3 to the power of d minus 2. We can change one of these 2s into a 4 and the other one into a 3 and keep the rest of our d minus 2 dice as a 3. This still gives us 2 squared, and now we have 3 to the power of d minus 1. And finally, we can have a couple of dice show a 6, and the remaining dice are 3s. This gives us 2 2s and 3 to the d power. And again, we have d plus 1 powers of 3. Let's skip ahead to 2 to the d power. If all d of our dice show a 2, then we don't have any 3s. If we have 1 6 and the rest of them are 2s, we'll again have 2 to the d power, but we'll get an extra 3. And so on, replacing each 2 with a 6 until we have 6 to the d power. This will give us a power of 3, that's d, for a total of d plus 1 powers of 3. We continue with the next power of 2, 2 to the power of d plus 1. Here we can roll a 4, and the rest of them are 2s. Adding up the 2s, we have d plus 1 of them and no 3s. Changing one of our 2s into a 6, we again have d plus 1 2s and 1 3. We can convert all of these 2s into 6s. So we'll have d minus 1 of them. This again gives us 2 to the power of d plus 1 and 3 to the power of d minus 1. Counting, we see now we have d powers of 3. Let's check the next power of 2. 2 to the power of d plus 2. We can take a couple of 4s, and the rest of them are 2s. This gives us the power of 2 for this case, and no 3s. If we replace one of our 2s with a 6, we get the same number of 2s and one more 3. Continuing on, replacing our 2s with 6s, we get the number of 2s that we need, and 3 to the d minus 1. So now, we have d minus 1 powers of 3. We'll continue with the two highest powers of 2. The second to highest is 2 to the power of d minus 1. We could have d minus 1 4s and then 1 2. This gives us 2 to the power of 2d minus 1 and no 3s. And then if we change this 2 into a 6, we get 1 3. And here now we're down to 2 powers of 3. And this is our last power of 2, 2 to the power of 2d. We'll get this if all of our dice roll a 4. This gives us 2 to the 2d and no 3s. So just 1 power of 3. Let's summarize this so we can do our counting. So when we had 2 to the 0, we had d plus 1 powers of 3, and the same thing for 2 to the 1, all the way up to 2 to the d power. When we went to the power of 2, that's d plus 1, we're down to d powers of 3, and so on. Our last 2 powers of 2 give us 2 powers of 3 and 1 power of 3. Recall that c was the power of 5 in the prime factorization of our product. We're going to sum over all possible values of c. So when c was equal to n, we found that we had no remaining dice that were not a 5, so d was equal to 0. When c is equal to n minus 1, d is equal to 1, and so on, with no 5s, and the remaining n dice are not 5s. This is the same as summing over all possible values of d from 0 to n. I'm going to divide up my counting by first adding up the number of powers of 3 in these first d powers of 2. That's d times d plus 1. And to that, I'm going to sum these values of d from 1 to d plus 1, and we'll use our formula for the sum of consecutive integers. I divided these sums up like this because this product is 1/2 of d plus 1 choose 2, and that's going to make our calculations a little bit easier. So again, we're summing as d goes from 0 to n of these two expressions. And I can rewrite this first term as 2 times d plus 1 choose 2, and the second term is d plus 2 choose 2. We can count these separately and expand the sums, factoring out the 2. When d is equal to 0, this is 1 choose 2, 2 choose 2, and etc. And our last term is n plus 1 choose 2. Our second sum begins with 2 choose 2 and ends with n plus 2 choose 2. This first term is equal to 0, so we can ignore it. And we can use the hockey stick identity, so we don't have to count all of these combinations. This part here is equal to n plus 2 choose 3, and over here we have n plus 3 choose 3. And according to the problem statement, this count is equal to 936. So now we're going to solve for n. Using the formula, this denominator is 6. To get rid of the fractions, I'm going to multiply both sides by 6. And I notice I have common factors here in n plus 2 and n plus 1, so I'll factor those out. And I'm left with 2 times n from the first term and n plus 3 in the second term. I can divide both sides by 3, and I'll find the prime factorization of the left-hand side and see if I can find this perfect square. Combining the prime factors, I can match these up to n plus 1 squared and n plus 2. This gives me n equals 11, or option A. If you'd like me to solve any math contest problems, please leave them in the comments.